Next, let's talk about density. Density is a factor defined as the ratio of mass and volume. At any given temperature and pressure, the density of a substance is a characteristic property and has a specific value. And this density is different for different substances. So the more common substances, for example, hydrogen has a density of 0.0000899 gram per centimeter cube. There are two units that are used. One is kg per meter cube, the other is gram per centimeter cube. So you can use any one of these units, so whichever you prefer. And oxygen as a gas has really less value. Notice that gases have very less density. But once you come to liquids, you start noticing that they have a higher density. And then when you go towards metals, they become really large. Right? So the larger the value, the more solidic the substance. So you end up from a gas to a solid. So at room temperature, these are the values at room temperature and normal atmospheric pressure of 1 atmosphere. Now, so let's try a problem. So you have lithium, a soft gray component, this gray solid with low density of any metal, and it's a key component in many batteries. So they have given you a slab of lithium weighs around 1.49 into 10 cube milligrams and has sides that are 20.9 milliliter by mm by 11.1 mm by 11.9 mm. So they're asking you to find the density of the lithium in gram per centimeter cube. So for density, what are the things we need? So we need mass and we need volume. So let's take this example here. So you have the mass given in total 1.49 into 10 cube milligram, and they've given you the length. So the volume, for the volume, they've given you the length of the sides. So it is 20.9 by 11.1 mm by 11.9 mm. So all of these are in mm. Now the first thing that we want to do is look at the density, what the units that they've asked. They've asked for it in gram per centimeter cube. So now we want to convert it into gram per centimeter cube. So let's copy these values. So these are the values that we have. So we want the density in gram per centimeter cube. So we want to convert first mass into grams. So mass here is given as 1.49 into 10 cube milligrams. So milli, we know that it's 10 power negative 3. So it becomes 1.49 into 10 power 3, and we know that m here represents milli, which is 10 power negative 3 into grams. So 10 cube and 10 power negative 3 gone. So we have 1.49 grams. So mass is in grams now. Next, volume. Volume is multiplication of all sides, but we know that they want it in centimeter. 1 centimeter is 10 millimeters. So for 1 millimeter, you get 1 by 10 centimeter. So multiply each of the values with 1 by 10. So we have 20.9 by 10 times 11.1 by 10 times 11.9 by 10. So you get 2.09 into 1.11 into 1.19. So these are the values. All of these values are in centimeter. Now we can multiply this to get the final answer. So you have 2.09 times 1.11 times 1.19. That gives you a value of 2.76 centimeter cube. Now we have the mass in grams and we have the volume in centimeter. So density is generally referred by rho or d. So d is mass by volume. So mass is 1.49 divided by 2.76. So this is gram by centimeter cube. So you have 1.49 divided by 2.76. that gives you a value of 0.539. So let me simplify it as 0.54 gram per centimeter cube. So this is the density of the lithium metal that we are using. So this is how we can do the problem. Always make sure that you convert things into the right units. Unless you convert things into the right units, you will never get your answer correctly. So if you want to convert from mm to centimeter cube, this is the value. But what if you want to convert 1 centimeter cube into 1 millimeter cube? So 1 centimeter cube to 1 millimeter cube, then 1 centimeter cube becomes 10 cubed millimeter cube. So 1 centimeter cube is 10 cube millimeter cube. So this is the conversion factor that we can use. Now let's talk about temperature scale. So freezing and boiling points of water in general Celsius and Kelvin or Fahrenheit scales are given in this diagram. Now if you take a general scale, you notice that the actual scale is graduated in different ways for different conditions, but the common conditions that are commonly used are the freezing point of water and the boiling point of water. Now when you classify a particular scale by the temperature scale, we notice that the divisions are what change. So you have the freezing point of water, this is the boiling point of water. Let's talk first about Celsius scale. In Celsius scale, 0 degree centigrade indicates the freezing point of water and 100 degree centigrade indicates the boiling point of water. In Fahrenheit scale, 32 degree Fahrenheit indicates the freezing point of water and 212 degree Fahrenheit indicates the boiling point of water. And in Kelvin scale, 273.15 degree centigrade indicates the freezing point and 373.15 degree centigrade indicates the boiling point. Now notice the difference in the number of total values. Between 0 and 100 there are 100 divisions. In Fahrenheit scale there are 180 divisions, and in Kelvin scale again there are 100 divisions. For example, let's say I want to know a particular value x in both the Celsius scale and the Fahrenheit scale. I'm going to call that temperature C in Celsius scale and F in the Fahrenheit scale. Now the difference in length from the value 0 is exactly the same for both the values. So the difference between the freezing point in terms of the length is exactly the same. But the only thing that differs here is the number of divisions. So what we could do now is we can take the ratio and make sure that the ratio stays the same. So what does the ratio mean here? So we are taking the ratio of the temperature that we use C and the 0 degree centigrade divided by the total number of divisions. So that gives you C minus 0 by 100 minus 0 is equal to F minus, here the 0 here is 32 in F. So F minus, it becomes F minus 32 divided by, it's going to be 212 minus 32. So it becomes C minus 0 by 100 is equal to F minus 32 by 180. Now when you cancel out, you get, when 25s and 29s. So you have C by 5 equal to F minus 32 by 9. So let's say if I want the value in C, for example, a particular temperature in Fahrenheit, I want it to be in Celsius, then the formula becomes C equal to 5 by 9 into F minus 32. But if I want a Celsius scale in Fahrenheit, then we can write F equal to 9 by 5 C minus 32. So 9 by 5 C minus 32 or 9 C by 5 minus 32. So these are the conversion factors from Fahrenheit to the Celsius scale. But if you want to convert from Fahrenheit to the Kelvin scale, what we can do here, so the Kelvin scale K becomes degree centigrade plus 273.15. This is the conversion factor for converting Celsius into Kelvin. If you want to convert Kelvin into Celsius, so Celsius becomes Kelvin minus 273.15. This here is the conversion factors for different temperatures. Now, let's take an example of these values. So notice that Kelvin is an absolute scale. So what does the word absolute mean? Is that there is a temperature called absolute zero, and there will never be a negative Kelvin temperature. That's why there is no degree sign. So we do not use the degree sign. Degree is only used when there is no absolute temperatures. For example, degree Celsius and degree Fahrenheit are not absolute scales, because Celsius scale is based on the freezing and boiling points of water. That's why the temperature scale is most commonly used across the world. Right? Fahrenheit is most commonly used in the US, and it has a different degree of size and 0 points. So the common way the measurement was taken is that 0 degree Fahrenheit so is the temperature of water mixed with equal amounts of salt at room temperature. So this here is the common temperature taken, but it's not appropriately graded scale. So that's why it's not commonly used across the world. Only in the US it's commonly used as of now. So these are the temperature factors that you can use. So let's take an example. A child has a body temperature of 38.7 degrees centigrade. The normal body temperature is 98.6. So we are asking you whether the child has fever. So what is the factor here? So we have 38.7 degrees centigrade, and here we are converting centigrade into Fahrenheit. So to convert centigrade into Fahrenheit, we need Fahrenheit value. So F becomes 9C by 5 minus 32. So it becomes 9 times. Substitute the temperature value in place of C. You get 38.7 by 5 minus 32. I'm sorry. The formula is plus 32. I'm sorry for that. So plus 32. Sorry for that. So you get a value of 101.66 degree Fahrenheit. So 38.7 degree centigrade is 101.66. It's still greater than 98.6 degree Fahrenheit. So the child has fever. Right? The child still has fevers. And if you want to convert from degree centigrade into Kelvin, so 38.7 plus 273.15. That gets you 311.8 Kelvin. Next, let's talk about significant figures. So every measurement includes some uncertainty. So the uncertainty here represents the rightmost digit of any quantity that is always estimated. So whenever you record digits, so they generally have certain and uncertain ones, and those are generally called the significant figures. So the greater the number of significant figures in a quantity, the greater its certainty. So the more significant figures you have, the more certain you are that it's a good value. So for example, if you look at this example, what would be the actual temperature on this scale? So notice that there are two ways of taking this. One way is to look at this and think like, okay, this is 32 and then you have 32.3. But are you sure it's exactly 32.3? The same way, look at the other example here. Is it 32.3 or is it 32.33? How are you sure that it's exactly 32.3? So the number of significant figures on a scale is what differentiates the type of value that we have. So you have 32 here, 32.33 is in this scale. In this scale we get 32.3. So the number of significant figures here is 4, the number of significant figures here is 3. So the higher the number of significant figures, the more certain you are that the answer is correct. So this is the type of example that we are trying to choose. Now, how do you determine whether digits are significant or not? So the first rule is all digits are significant except zeros that are only used to position the decimal point. So whenever we use the decimal point, so make sure that you measure quantity has a decimal point. So always start at the left and move right until you reach the first non-zero digit. Count that digit and every digit to its right as significant. For example, if you have a value of 0.0015, all of these values cannot be counted as significant figures. Always choose the first non-zero digit. So 1, 2, 3, 4, and then only here you start counting the significant figures 1 and 2. So the total number of significant figures in this problem is 2. Next, zeros that end a number are generally significant. So for example, if you have a number that's 1.030, it still has 4 significant figures, provided there is a decimal point. If there is no decimal point, then there is only 2 significant figures. So for example, if you want to write that this is 5300 liters, then this has 2 decimal points. But if I write 5300.0, then this has 5300 point liter, then this has 4 significant figures. So that dot causes it to change your number of significant figures, and you are saying that this is a certain value and not a approximate value. Now, so use the principles that we talked about and try to find the number of significant figures in each of these. So pause the video right here and try to solve this problem. So we talked about significant figures. So let's talk about significant figures specifically for arithmetic operations such as multiplication and division and addition and subtraction. So let's start with multiplication and division. So the answer generally contains the same number of significant figures as there are in the measurement with the fewest significant figures. For example, in this measurement, this has 2 significant figures, this has 2, and this has 4. Now, the final answer should have the least number of significant figures out of all of these. So the least number is 2, so the final answer should have 2 significant figures. So that's why we round it off to 2. So what we do here is we round off the numbers. So to round it off, what do you do in rounding off is, if you have, for example, let's take this number 23.4225. If I want to convert this into 2 significant figures, what we do is we start elimination or rounding off the significant figures. So we start with the last number. Check if the number is greater than 5, less than 5, or equal to 5. So here the number is equal to 5. If the number is greater than 5, add +1 to the number before or the preceding number, right? So if it is less than 5, add 0. If it is equal to 5, only then, if the number before it is even, add 0. If the number before it is odd, add +1. So the number before it here is 2, so this can be eliminated directly. Now let's look at this number again. 2 here, so this is less than 5, so we can eliminate it directly and add 0 completely to the previous number. Next, again 2 here, so we have it's less than 5, so you can eliminate it directly without adding anything. Next you have 4 again, 4 is also less than 5, you can eliminate that directly. Now we are left with 2 significant figures, so 23 centimeter. So this is how you write the final answer. So this is the idea behind multiplication and division. So when you multiply, always look for the lowest number of significant figures out of all the numbers that you are multiplying, and that should be the number of significant figures in the final answer. Next, for addition and subtraction. Addition and subtraction do not focus on the number of significant figures, but focus on the number of decimal places. So the final answer should have the fewest decimal places out of all of the decimal places possible. For example, here we have 83.5 and 23.28. Notice that here the least number of the decimal places here there is 1 decimal place, there are 2 decimal places here. So the final answer should have the least number of decimal places, so it should only have 1. But the final answer here is 106.78. So we only want 1 decimal place. What do? Again, we start rounding off. So we look at the last number 8. 8 is greater than 5. So what do? to the number before it we add plus 1. So what happens now? This goes out and the answer becomes 106.8. So this is where you get 106.8. So the same thing with subtraction as well. Always use the least number of significant figures possible. So when you round up this number here, 9, so it's greater than 5, so we add plus 1. So this becomes 8. Right, so this becomes 8. Again, 8 here is greater than 5, so we add 1 again. So it becomes 9. So 863.09. Again, 9 is greater than 5, we add plus 1 to 0. So we get 863.1 mm. So this is how you do rounding off, and this is also how you do for addition and subtraction. So to summarize, for multiplication and division, so use the fewest significant figures of the numbers being used. Okay. For addition and subtraction, use the fewest decimal places of the numbers being used. So focus on the term the fewest significant places and fewest decimal places. When addition and subtraction, we focus on the fewest decimal places. When multiplication and division, we use the fewest significant figures. So remember this topic because we are going to use this throughout organic chemistry, general chemistry and everything again and again. So we already discussed rounding off, so I am not going to discuss it again. So let's continue and let's talk about exact numbers. Exact numbers generally have no uncertainty associated with them. So numbers in general by definition, for example, 1000 milligrams is 1 gram, 60 minutes is 1 hour, 2.54 centimeters is 1 inch. These are numbers that may be exact by count, exactly 26 letters in the alphabet. So exact numbers do not limit the number of significant figures in a calculation. So exact numbers cannot have any influence on the number of significant figures. So for example, in this case here, we have an exact, we try to do this and try to find out the total number of significance in the final answer. So use this as a problem and try to solve this problem. Next, the final concept, precision, accuracy and error. What is precision? Or whenever somebody says, how precise are you? So, or tell me precisely what you want. It basically means that it basically says that how close the measurements are in a series to each other. So there is a slight difference between precision and accuracy. Precision refers to how close the measurements are to a certain value, and accuracy refers to how close the measurement is to the actual value. So precision refers to each other and accuracy refers to the actual value. So whenever you have a systematic error, it produces values that are either all higher or lower than the actual value. So this error is called as the experimental error, and there are random errors that produce values that are both higher and lower than the actual value. These are called random errors. So for example, in this trial here, when they are measuring the mass, notice that all of the mass values are really close to 25. So here this is an example of where they are also close to each other as well as they are close to the, so in this case they are close to each other and they are also close to the actual value. So when they are close to each other, we are saying that these measurements are precise. When they are close to actual value, we will say that these are accurate. In the same way, let's look at this example. Here, all of the values are really close to each other, which means that they are close to each other. But they are not close to the actual value. So this is an example of being precise but not accurate. So this is an example of being precise but not accurate. Next, this is an example of a random error where you end up getting both the higher values and lower values from the actual value. Systematic error is an experimental error where you either get really high values or really low values. So you either get only one side values. So this is an example of systematic error or experimental error. So that ends chapter 1. So I will see you again in the next lecture.